Welcome to our next session, implementing DNP3. Graham said that he'll take questions either during or after on the subject, but this should be an interesting subject. Go ahead and take it away, Graham.
Okay, welcome everybody. Hopefully going to speak for about an hour on this subject. Meander around basically an introduction to DNP3 and why you might want to use DNP3 in your systems. And then a little bit about how DNP3 works, and then a bit about configuring DNP3 in VTScada, and then tricks and tips, things you should do and things that you shouldn't do with DNP3. So the start off introductory slide there with my name. I've been with Trihedral 20 years. In fact, I wrote the original DNP3 driver for Trihedral before I'd even joined the company. I did it as an external project 2 decades ago for a customer in Brazil. And I've maintained the DNP3 drive within VTScada with the help of my colleagues for the last 2 decades. So certainly at the protocol level, I like to consider myself very experienced. Not necessarily so much in the field deployment level. I tend to get information when customers are running into issues. So I don't see all the systems, hopefully. They're running nice and smoothly out there. And the other DNP3 aspect that I'm involved in, and it's what got me into Wireshark development, back when I was developing the dissector and we were able to move away from serial onto IP networks and could capture DNP3 traffic. There wasn't a dissector for DNP3 in Wireshark. So that got me introduced into Wireshark, and I've also been working as a core developer in Wireshark in my own time ever since, again, for nearly 2 decades. So what is DNP3? A little bit of history of it. It was created in the early 90s by Westronic, a Calgary-based company, who did their own line of RTUs. And they were reasonably experienced in making RTUs that could speak multiple protocols. But they got fed up with implementing all these proprietary ones and moved on to create their own one. And they did it quite uniquely, I think, for industry at the time. They decided this would be an open protocol, that it wouldn't be proprietary, and that they would hand over control of the protocol to the community. So they created a DNP3 users group, which still exists and runs today, and is the shepherd of the DNP3 protocol. And they maintain and produce technical information, any amendments needed to the protocol. Back in 2012, the protocol was standardized, as it were, through IEEE. So it does have an official best name now, IEEE 1815-2012. So you can go off to IEEE and buy the very expensive standard from there, which is exactly the same as the standard you get from the DNP3 users group. You still have to pay to join the DNP3 users group, reasonable amount of money, I think it's about $300, that gets you access to all the protocol specifications. And originally it was used in the electrical industry, and it has some unique features, I think, for the electrical industry, some of their requirements. But it's spreading out now beyond the electrical industry, spreading into water industry. And back in 2003, the UK water industry, slightly different setup to what you have in the US. It's several, I think 8 or 9 large private utilities that they felt that they were getting locked in with vendor lock-in. So they adopted DNP3 and some extra specifications over the top of DNP3 for the UK water industry telemetry standard, WITS as it's called. And the one-line summary, I tried to come up with a one-line about why you would use DNP3, and I think I found this in a document somewhere. So it's a SCADA protocol that uses report by exception, and that gives us robust and efficient communication of telemetry data. In the end, as operators of the SCADA systems, that's all you're interested in, that communications are robust and efficient. I think DNP3 does have some features that work really well to achieve that. So I did some more historical notes. I'd actually found out a few things myself. I didn't know at this when I came into this. Obviously working in it for 2 decades, I wasn't too interested in how it came about. As I mentioned before, Westronic invented it, and they definitely used certain aspects of other protocols that had been laying around at the time. IEC 870, which I'd also worked on in the 90s before joining Trihedral, was an IEC protocol that didn't actually define application layer stuff, but basically it was the lower level data link protocol specifications, and Westronic used that for DNP3. So those protocols are similar. It's now called IEC 6870-5-101, or 104 if you're going over TCP. So at the very low level, those protocols are similar, but as you move up the protocol stacks, they differ quite significantly, such that they are not interoperable. They're similar but not interoperable. For bandwidth, again, at the time in the 90s, links were very low speed. So it's very important to limit the bandwidth usage, get the maximum data through at the time. And so that influenced the design of DNP3 protocol. And they were also very concerned about having too many layers in the protocol stack. There was at the time a fascination with making protocols ever more complex, and so they made a significant effort to reduce it. Although they did make one rather odd decision that I won't really cover today. It's a technical thing in the protocol, so that's why I say they've got 2.5 layers, because this one layer is just 1 byte that achieves a very significant thing, the transport function, but isn't really a protocol layer. And then probably the most contentious thing I think about DNP3 today is in the electrical industry, they were really focused on reliability of their SCADA telemetry. And so DNP3 used the most secure frame format, very low level frame format available at the time, which was lifted from IEC 6870 and frame type 3. And what this frame type dictates is lots of CRCs. Every 16 bytes of data, there's a 2-byte CRC. So there is a fair amount of overhead within a DNP3 data packet with all these CRCs. But if you imagine, it was originally for use in the electrical industry with lots of EMI over serial links. The reliability of the data and accuracy of the data was key to them. And it also supports select before execute, or select before operate, so that, for instance, operating a digital output would be done in 2 phases. You would send a select command, and then you would send an execute command. And the reason for that was, it was again more reliability, that you couldn't have a bit flip or something else in the transmission of the operate. So the 2 select and execute commands had to coordinate and show that they were operating the same, exactly the same point in the outstation. DNP3 also supports direct operate as well, so you don't have to use select before execute unless you want to. And it's actually called DNP3 because Westronics apparently internally had previous DNP1 and 2 protocols, and now its official name, as I mentioned there, is DNP3 followed by the name of, the year in which they published the test spec for that particular version. So DNP3 2012 is the latest one. So we've covered a little bit of background about where it came from. So why would you consider using DNP3 in a SCADA deployment? As I mentioned with the UK water industry, vendor independence, I think, is a key aspect here. It's an open protocol that any vendor can implement it. You don't have to pay money to implement it. Obviously, you want to get the specifications, so it's just a few $100s, but there's no licensing fees thereafter. So allowing vendor independence in that way means, as SCADA system operators, you're not linked into a particular vendor's hardware and software. That you have the ability to mix and match, as it were, for best of breed. Another thing I think key to DNP3, certainly at the time compared to other telemetry protocols, I think it's got a rich set of data types. So we have distinct data types for all sorts of things, binary, input, double-bit binary input, analogs of various 16-bit, 32-bit, float, double, counters, strings. So there's a rich amount of data types, which is contrast, say, with Modbus, which is obviously on the go at the time, whereas Modbus's view, everything's a 16-bit register. And you have to manipulate that 16-bit register or multiple registers to make larger objects such as a float or something like that, or even transmit log files. DNP3 also has built-in file transfer, so you can transfer configuration files, data files, and anything else to and from the outstation. Second key takeaway, I think, for DNP3 for me is events. So DNP3 is a report by exception or report by event protocol, so that unlike Modbus, for instance, where you have to scan all the registers and regardless, you have no idea whether the data's changed or not, you have to poll them all the time. DNP3 outstations can generate events as data changes in the outstation. And so that means that your data traffic can be configured such that the only data between the master and the outstation is actually data changes. So you're making very efficient use of your communications bandwidth there if you're only transmitting changes. And as well as transmitting data changes by events, these can be time-stamped in the outstation. Again, in the electrical industry, they were looking at rapidly changing events, circuit breakers and reclosers happening quite quickly. So DNP3 timestamps down to 1 millisecond. And the outstation can buffer these events. So if you're unable to communicate at the time with an outstation, say there's a disturbance in your distribution network and something goes off, the outstation can capture those events in a buffer and retain them for when the master can actually get round and communicate, or if you configure it, the outstation can send them to the master as and when it likes. So this means that you don't have data loss just due to brief comms outages or anything else, and also that the granularity of your data changes is limited only by the 1 millisecond clock in the DNP3 outstation. So in Modbus, when you poll a device, you can see a data change. If you don't get down to poll for the next 5 minutes, data could go on and off in that period, and you've got no idea. DNP3 will buffer all those events, and when you read back those events, you'll see that that motor or that pump has started and stopped and started and stopped. And you'll have timestamp accuracy down to 1 millisecond. As I mentioned there, yes, outstations can optionally transmit these events to the master, so the master doesn't even have to go and ask for them. They can be transmitted as required by the outstation. And so I think these are the key aspects to me of DNP3 and how it is useful in a SCADA environment. Accuracy of reporting of events with timestamps without the limitations of having to poll data at a very high speed to get that granularity. And that's particularly important when you're using a shared communication media such as radio. If you've got 200 stations on a radio and you know you have to poll them all sequentially, it takes a long time to get round back to station 1 again. Well, with DNP3 over radio, then you're minimizing only the data changes in the actual stations. And so therefore you'll get a much greater update rate of actually changed data. A little dive into the basics of the DNP3 protocol. There's a bit of startup communication between a master and an outstation. It's laid down in the protocol specs what you should do, and basically does a couple of things to initialize the outstation, set the clock in the outstation if it needs to be set, and read any pending events, because of course this may be the master just coming up and the outstation's been running all the time while the master was off. The master is also in control of whether the outstation can send unsolicited messages. So by configuration in the master, you can enable and disable those. As I mentioned, it sends any time synchronization required. And then generally, the system goes somewhat quiescent, and it's just waiting for data changes. Usually we configure the master station in DNP3 to query the outstation periodically. 10 minutes or so, you're just making sure it's still alive and asking for any events it has. You can poll quicker if you wish, but I usually find 10 minutes or so is quite reasonable. And you're actually, instead of asking directly for a particular data item, say as in Modbus you would ask to read a block of registers, in DNP3 you ask for a class of events or a class of data. And so it's a simple request for classes 0, 1, 2, and 3, which I'll come on to in a little. And then the RTU outstation will respond. Classes 1, 2, and 3, as I mentioned, are used for event data. There's no priority ordering between the classes. You can allocate tags or points in the outstation to any particular class that you wish to use. The main reason for segregating them into different classes is the outstation configuration can treat those classes separately on reporting via unsolicited message. So the outstation could maybe immediately report class 1. They might be high priority digital status changes, and then it could hold off reporting class 2 until sufficient events are gathered because they're not quite so important. Something like that. So it gives you some options there. That's the allocation of the tags to the classes is generally outstation configuration item. The master can't affect that. And the other class that's generally used in DNP3 is class 0, which is called the static data. Although I think that's rather misnomer, static. It's actually the current value of all points in the RTU configuration, in the outstation configuration. So when you do, that's often known as an integrity poll. That's certainly the configuration item in VTScada. And so you would configure up to do an integrity poll, say maybe once a day. And the idea behind that is you're picking up data that isn't reported by event, and you don't consider it that important to know. Again, within VTScada, we can configure integrity polls at any periodicity that you would like. Same as with the polls for classes 1, 2, and 3. DNP3 is a request-response type protocol. So the master will generally initiate a communication by sending a request out, and the outstation will respond. And the response might contain multiple fragments. A DNP3 message, generally it's accepted, can be up to 2048 bytes. And so because of the low-level frame type used by DNP3, that gets split into multiple fragments. And so the outstation will send these messages in fragments, the master station will reassemble them, and if there's event data from the outstation's events buffer, then the outstation should ask for confirmation from the master that it's received those events. And that's a positive confirmation that the event data has been received by the master, and then that allows the outstation to remove those events from its buffer that they've been dealt with. So this means that we really shouldn't lose event data in DNP3. The only option for losing event data is if we're unable to communicate with the outstation for such a period of time that the finite space in the event buffer has overflowed. Each outstation can only have so much memory for events, and if it's generating events at such a rate and unable to communicate with the master, eventually that event buffer must overflow. And at that point we will lose some events. It's down to the outstation whether it deletes the oldest events from its buffer or doesn't add the newest ones. It's indeterminate. Or we get a status signal back from the outstation that says the event buffers have overflowed, but there's nothing we can do to retrieve those events. So that would really be an extreme scenario where the rate of event generation in the outstation exceeds the ability of the master to actually connect to the outstation and retrieve that event data. So I was just going to quickly fire up Wireshark here and just show you a couple of packets here. So we can see there we have a communication from the master to the outstation, read of class 1, 2, 3, and then the outstation back to the master response. So that's a, as I said, request response protocol, fairly simple. And then down in the bottom corner here, if I expanded it, we can see the various parts of the DNP3 protocol, the data link layer, the transport, and then finally the reassembled application layer. I won't go into this too much because these are all quite low-level details that unless you're actually debugging DNP3, you don't need to know too much about it. So we have the message that the master's generated, and then we have a look at the response here, and this is actually a null response. So what's happened here is the master has asked the RTU, the outstation, do you have any class 1, 2, 3 data? And the outstation has returned a positive response that says, no, I don't have any data for you. So that's two simple polls, simple poll and a null response event. If I then pick another capture, so this time we can see there's a read class 1, 2, 3 and a response, and then following on that a confirm message back from the master to the outstation. And if we look at the response, and then we can see in here there's some response data objects and there's 16-bit analog change with time, and expand that out, and then we finally see in that line there exactly what has changed. So it's point number 1, its value was -32766, and it had a timestamp way back in November 2016 when I made that capture. Wireshark unfortunately shows it with a bit more resolution than it actually gets. A few more digits there that we don't actually get, but it's accurate down to the millisecond and whatever drift is in the RTU clock. So the master will set the time in the outstation, or the outstation can use its own time source if it has a GPS receiver or something else like that. And then after that time has been set, then the outstation clock may drift a little, but the granularity of timestamps is to a millisecond. Probably more critical in the electrical industry than the water industry. And so this one is showing the startup sequence. This is a typical VTScada startup sequence. I see this a lot when looking at captures from customers. So we'll just run through it here. I won't go too much into the details of it. So we do a low-level test of the remote link. Is it okay? The outstation says yes. First thing we do is turn off spontaneous or unsolicited messages. During initialization, we don't want events to be sent to us. We'll gather them afterwards, but we're turning that off. The outstation says OK. The outstation has actually sent back in that OK there a significant flag, which I shall just show here. It's called the internal indications. So every response from the outstation has an internal indication. It's called the IIN. And that indicates various, there's 16 bits of information there about various states in the RTU. So we can see this one here has told us the device is restarted. It needs a time sync, and there's class 2 data available. So there's a whole number of these indications here. So this device here is obviously just powered up. And so this is the first communication with it by the master. And so the master is going to see that device restart, and it's going to clear that flag. It has to write back to the RTU to clear that flag. So these are the next two here. Write to the internal indications and set the response. And then because of the next flag in the IIN there, time sync required, the RTU is asking for time sync. So we do a couple of commands here. We measure the delay between the two, so that we try and measure the length of time it takes to send a message and get a response back. And we use that, we halve that delay time and add that as an offset to the time that we're going to write out to the device. And we can see here we write the time and date to the device. And then we actually do it again. Interestingly, I hadn't realized this at the time, that this customer's device, this was a outstation vendor was asking me to test something for them. Their device, after we set the right time and date, if we look at the response from that, so now, remember now, we've just set the time and date for this device. But if you look at the IIN coming back, it still says time sync required. So we've set the time sync, and it hasn't cleared the flag. So as the time sync required flag is still set, we do another delay measurement and write it again. Unfortunately, in the subsequent response, they've cleared the flag. So no time sync required. So that RTU there is a little bit of an implementation issue in DNP3, not clearing the flag quick enough, and causes us to send a few more messages to set up the date and time. And then after we've set the date and time, we read back events and static data. Now, that's actually reading. It's quite significant the order that the class numbers are shown there, because that's actually the order in the request, and that's how the outstation should respond to that. We have changed that. As you saw, this file was from 2016. It's actually, we do a class 1, 2, 3, 0 read. And the reason for that is we ask for the events first, 1, 2, and 3, and then 0, the static data. And then we can see here, this is the example of a fragmented message. So all these are fragments, and it tells us it's fragment 0, 1, 2, 3, 4, 5, and there's fragment 6 in there, and Wireshark has reassembled them all into that one response. So that one response there now has the entire DNP3 message in, and we can see there, if we look at this tab here in Wireshark, in the reassembled data there, it's very small print, sorry about that, says it's 1264 bytes of DNP3 application message. So we've taken all those fragments, which are all 200 odd bytes each, reassembled them into one large message. I won't really, well, I'll just quickly expand that response just so you can see that there's a whole heap of data objects in there. You can see there's all analog change events with time, and then scroll right down. At the end, we should have some static data. See here, these don't have times now, so we know that these are static data. So these are various analogs values. And because there was event data, the master has to confirm it. So it sends back the confirm to the outstation. That allows it to clear its event buffer. And you'll notice as well, the other item in that response, it's IIN there, the internal indications, is all 0. Because we've now read the events, there's no class 2 data available for us to read, so it's a totally clear and all good IIN value there. And then the last command of the initialization, if you've enabled it in the master station, is to turn back on unsolicited or spontaneous messages. So now the outstation is initialized and can send us event data as required. And then we have communications coming back the other way. This is where the outstation is going to initiate communications to us because of an unsolicited message. So the outstation will send us this message, possibly multiple fragments, depends how big the application message is, and then the master sends back the confirmation. As I've discussed previously, this whole confirmation idea allows a positive acknowledgement that the master has received this event data and allows the RTU to clear its buffer. The size of the event buffer is not dictated to by the protocol. It's down to individual outstation manufacturers, their hardware and their software limits the size of their outstation event buffer. Usually there's room for a reasonable amount of events. You have to consider what your likelihood of a comms loss is, and that identifies how much sort of a buffer you would need. So now I'm looking at how we configure up in VTScada to use DNP3. So VTScada can only be a DNP3 master. For some protocols and our drivers, we support acting as an outstation or a slave. Not for DNP3, we can only be a master. But it is a standard built-in driver in the VTScada product. And so to communicate with a DNP3 outstation, we need a DNP3 driver tag and we need a port tag. DNP3 can run over serial, TCP/IP and UDP/IP. And then to configure up the driver tag and the port tag, some essential elements of information. Fairly obviously, if you're going over IP, you need the IP address and port numbers and so on like that. DNP3 has an IANA assigned port of 20,000. That's the standard port for DNP3, but we do support running over any other port that you care to use. And if you're running over serial, obviously you need to know your serial communication parameters, baud rate, start, stop bits, and so on. So that's your transport media. You need to know those details. And then you need to know from the outstation configuration document some particular items. Within DNP3, there is, in the protocol spec, it discusses a document called a device profile. And vendors are meant to produce this device profile. Often it can be produced by the vendor's configuration software, and that will list all the DNP3 commands that the device supports, all the options in DNP3 it supports, all the data types, and also should have the points list for the RTU, so listing the indexes of each tag. I didn't really cover that earlier, but in DNP3, sorry, I do cover that a little bit further on when we discuss I/O addresses. But DNP3 points, we have a group, a variation, and an index. So the group and variation indicate what type of data it is, and the index is the actual address of it, very similar to a Modbus register address. So within your device profile, hopefully your vendor's given you, or whatever other configuration documents they've given you, you will have such things as the outstation DNP3 address, and if it's sending unsolicited messages back to the master, quite often it wants to know the master address, although some other outstations will just send data back to the last master that communicated with them. And you'll have hopefully all the I/O addresses that they're using. So I've displayed there the communications tab. I've not bothered with the ID tab because we all know that's the same for all VTScada tags, so there's nothing interesting on that. So on the communications tag, this is most of it is to do with the low-level communications. So as I mentioned earlier, we need a port. So you need some type of serial port, TCP port, UDP port. And then you'll have the timeout. So this is the timeout for receipt of a start of a response of a message from the outstation. So obviously I can't give you any good values there because it all depends entirely on your deployment. The values on a LAN will be much smaller than the values on some kind of cellular WAN network that has very slow communications. Oftentimes, cellular modems take a little while to pick up and respond, so you might have to push the time limit out a lot. The RTS key-off delay is a bit of a hangover from serial days or radio modem days. Unless you are doing something with serial or serial modem, then you'll leave key-off delay to 0. Essentially, that held the RTS line high on a serial port until all the data had gone out. And then it would drop the RTS line, which would drop the modem carrier on the radio. So you wanted to make sure there was sufficient just past the end of the message to allow the signal to go out. So you had an adjustable RTS key-off delay. As I say, unless you're doing serial these days, it won't be of any use to you. And then the parameter here, message fail time. Again, this is more specifically for shared media systems, such as radio systems. Where you've got all your devices on a shared media, you can only communicate with one at a time. And so if you've got a device that's failing and you're retrying, then that's going to hold up your communications with all the other devices because your communication media is shared. Your radio can only communicate with one at a time. So the message fail time allows you to sort of put a back-off time on a particular driver that's failing. So after the driver's failed to communicate, it won't communicate again until that message fail time has elapsed. So you can put a figure in there to make a failing RTU not hold up your scan around all the other RTUs on your shared media. If you're using point-to-point media, such as TCP or UDP, then again, message fail time should be set to 0. A couple of other options here. Retries. How often the master will retry a message. I'm never entirely certain which way we should go with that. For LAN links, TCP, I don't think you need retries. TCP itself will retry if a segment's dropped. And for a LAN that's high reliability, I don't think retries get you anything. Maybe over a radio, where you could be affected by interference, it's worth having 1 or 2 retries on. And possibly for UDP, because UDP has no inbuilt packet retransmission capabilities. So it's a bit of horses for courses. What I find does happen is people set retries up to some fantastic number of 10 or 20, thinking that's going to improve communications. But if your communications path is poor, such that the device can't respond, you're going to do 20 retries for no effect whatsoever. So I tend to keep that a fairly low number. The hold parameter there, fairly common amongst VTScada drivers. When the driver fails to communicate with the remote device, generally drivers will invalidate the data. So all the data will go invalid from all the tags connected to that driver because it's indeterminate. We can't communicate with the device. We've got no idea what the value is. Some people don't like that, and so the hold option just leaves the data in the tags at the last value. So when you get a communications fail, the tags will not show any change in value. Again, most people should be leaving that off, I would have thought. Redundant multiplexer connection. If you've got a redundant multiplexer in so that there's 2 paths to your outstation and the multiplexer can choose between one or the other, that just signifies that you've got that type of connection, and it minimizes the traffic to the, normally the 2 paths are treated as primary and standby, and it minimizes data traffic down the standby, just to only check that it's alive and not actually do any data transfer. And then this last group on the left, which I've been avoiding a little bit, these are to do with the scenarios where the device can initiate connections back to you. So in the old days, it used to be modem dial-up, where the device could dial into the master. In these days, it's more likely to be TCP, where the device can initiate a TCP connection back to the master. And to do that, we need an IP network listener tag that listens on the master station for inbound connections on a particular port. And then when an inbound connection is received, it goes through all the drivers connected to its group. Each listener tag has got a group. All the drivers register with that listener tag. They'll get given this bit of communications and they'll determine whether it's for them or not. So you can have hundreds of DNP3 drivers all listening on the same port, and when a particular outstation communicates in, the system will find the correct DNP3 driver instance for that outstation. And so these allow you to configure up IP network listener groups to allow those inbound communications, and you can also do restrictions on which IPs, which remote IPs are allowed to connect to you. Very specific configuration if you're doing that type of thing, but it does work very well in those scenarios. So the data link tab is now we're moving on to actual DNP3 configuration items, or within DNP3 protocol. So we have two addresses. There's the address of the master and the address of the outstation. Some outstations won't communicate with a master that's not got the address they expect as a security measure. So you have to get the master address right. There's no magic master address that you can put in that will work all the time. Again, that's down to the outstation configuration. And then you have the actual outstation device address itself. These are 16-bit numbers, and you've got free use of 0 to 65,000 and a bit. There's a few reserved addresses here, which I'll come on to. So you've got lots of different outstation numbers. Again, outstation addresses are much more important when you have a shared medium such as radio, because you need to be able to address each individual device over the same transport medium. Where you've got point-to-point links like TCP, then the station's IP address really serves that. So the station address doesn't matter too much, but you will need to get whatever's configured in the outstation there. And then we have the options. Instead of using a single address, DNP3 supports broadcast addresses. So you can send a message to all devices. So, and there's three particular different types of broadcast addresses, and they depend upon whether the device will acknowledge the master's broadcast message. We do have a customer using that to simultaneously broadcast a message, and so all their outstations then play a loudspeaker alarm announcement, and they're all synchronized because they're generated by a broadcast. And then the last checkbox here on this tab, data link confirmation. Within the IEC frame type 3 at very low level, there is the ability to require the remote end to send an acknowledgement every time it's received a packet. Very similar to TCP ACK. You can turn it on and devices may support it and they may use it, but you end up sending a lot of useless bytes down the wire. I don't really see what it achieves these days. It's there mainly a compatibility thing, but I would suggest that there's no need to turn that on these days. A question at the back there, go ahead. Oh, sorry, the question was, does TCP send a response without that check? Well, this is at the DNP3 layers above TCP and UDP. So this does not affect UDP or TCP behavior. This is sitting on top of that. So that won't affect the TCP ACKs at all. Within VTScada, we can't do anything with the TCP ACKs. That's all handled by the Windows TCP stack. So we're entirely reliant on that and can't affect that. So this is purely, so if you turn this on a TCP network, you would send a message, you would get a TCP ACK, and then the device would send a DNP3 ACK, and then the master would have to send a TCP ACK back for that. So you've got ACKs at multiple levels in the stack flying all over the place. I guess it was useful in the days of serial links, but not these days on IP links. And then the options tab, I think this generates quite a few questions and issues, I think. I've configured this here generally how I like to see the systems. You can control when you're polling for events whether you want to read a specific class or not. It's lost in the midst of time why we actually added that. I don't know why you would actually want to disable reading a particular class of events. If the RTU or the outstation is generating events of a class and you don't read them, it's going to overflow its event buffers. Why would you want to do that? So I can't see any sensible reason for disabling those. The one thing I've come across is, oh, we've got an RTU that's generating far too many class 3 events, so we don't want to read them. Well, why not reconfigure the RTU to not generate those events? So leave all those as they are. So we're enabling class 1, 2, and 3 reads. And then this is the periodic integrity poll, as I mentioned, the static data. Generally, I think you want that turned on. And so that will read the static data once every poll period as defined in this field here. This RTU interval is the period at which we'll send the class polls. So we've got 2 poll intervals there, class polls and integrity poll. And if you have data in your RTU that is not reported on by event, so you've configured it to not send events, then the only way in a normal system to get that data back is via the integrity poll. So if you've unable to come to an agreement with your customer for analog deadbands, so you can't set deadbands on analogs, and so therefore you think, well, we shouldn't really report them by event because they'll be going off all the time, then you're really going to have to reduce the integrity poll period to the rate at which you want to retrieve those non-reported data analogs. This field here is for a specific type of RTU, which I think only 2 people at a conference will ever come across, the Xylem people. It's one of their specific RTUs. It's actually part of WITS. WITS has a specific history file format, the UK water industry telemetry standard, and we added that to read back their history files. Most people, you can leave that alone and it won't do anything for you. Here now is where we configure unsolicited data. And this one I think you should be able to touch whether you're going to use unsolicited data or not. It's a fairly simple binary choice. If you don't enable it, then you'll only be getting data back at the rate that you've configured your check RTU interval for events and the integrity poll interval for static data. Whereas if you do enable it and the device is configured to send unsolicited messages, then you'll get much better reporting of event data, much more prompt. We won't lose any more or change it, but it will be much more prompt appearing in the master station. You can, again, same with the class polls there, disable individual unsolicited data, but again, I can't conceive a reason why you would want to do that. If the device is generating data, event data, then really you should want to go and read them. What I will say is you could turn 2 of those off and leave 1 on. And that would mean that the one that you enabled, that would allow the outstation to report that unsolicited data. And then in its IIN, that internal indications flag that I told you, it would tell you that there's data for the other classes. So then we would automatically send a class poll for that data and read that back. But all you're doing with disabling those is increasing the time before we pull those events back. I think it's better just to leave those enabled. I'd be interested if anybody's come up with good reasons why they want to disable those. We have a set radio box here to what happens when we reconnect. So if we lose communications with the device, or we allow the communications channel to drop because we've got no data transfer, When we then connect back to the device, we've got a number of actions we can take. We can do nothing. We can send a class 1, 2, 3 poll for events, or we can also send a full integrity poll when you connect back. So it's your option what you want to do when it reconnects. And then we've got a few odd little miscellaneous ones. These are more general driver options in VTScada, where we remember the last written output value, and then we can enable it to be auto rewritten on master startup. Not entirely certain what those are used for generally, but we do them there. And this one is always a big bugbear of mine in DNP3. When DNP3 originated, they did not specify in the protocol spec what the time zone was of timestamp data on the wire. And that meant people were free to make their own choices. And that led to issues of, well, what time zone is it? Then in 1999, they revised the spec and they said all timestamps in DNP3 over the wire are to be UTC, which makes great sense to me because UTC doesn't have daylight savings time and we all know where we are. Internally in VTScada, we store history in UTC. So if you're going to send us stuff in local time, we have to convert that to UTC to store it. So the only reason for that checkbox is compatibility with really old RTUs, outstations that are more than 20 years old, that can't be configured in anything other than local time. So you really want, in my view, leave that off. And then if the master, if VTScada is setting the time in the outstation, it'll set it to UTC. And when it comes back, you won't have to do any conversion. And you won't have any possible errors around DST start and end. Because the main issue with using local time, at the end of DST, when the clocks go back, you can have an event reported that's got the same timestamp as something an hour ago. So if you leave that off, the timestamps will be in UTC, and we won't have that issue. I've heard customers have issues with that because they say, oh, my HMI at the outstation then shows UTC time, and that's no good to me. Well, you should configure your UTC, you should configure your HMI at the outstation to convert from UTC to the local time there, not put the PLC into local time. You're welcome to set that, but then bear in mind at the end of DST you might have odd timestamps. Your choice. A little bit about the complicated DNP3 addresses. Sometimes I wonder what I was doing 20 odd years ago. Why did I make it so complex? But basic format is we have three main portions separated by slashes and a suffix there, various types. And so we have group, and that's a DNP3 term. The group is the main data type. So an analog input is a group, and a a binary output or a binary input are different groups. So that's an integer number which indicates the group to be used. The variation is, as you might imagine, a subtle variation within the group. So for analog inputs, a variation 1 is 16 bits and 2 is 32 bits and so on with floats and doubles. So you can have those different variations. And then the last bit there, the index, again, numeric value, that's your DNP3 point address or index in the outstation. And then we have a suffix here, :NS. And if that is set, that indicates that you are not scanning. NS is not scanning, and that means that you're not doing a direct read of that address as per Modbus does. So unfortunately, that really should be the default, and we should be putting on a suffix of enable scanning, because that's the oddball case that we don't really want, not many people use, but unfortunately the default would be scanning, so we have to generally put that suffix on. And that means then, if you put that on, the data will only be retrieved by class polls. Quite a lot of RTUs won't even support direct poll of tags. They only support class polls. So unfortunately, you have to add that NS pretty much all the time. So I've done a couple of examples here. An analog input, index 24, not directly polled. So group 30, variation 0. Variation 0 really means I have no idea of the variation, just give me whatever you have. And VTScada will correctly read it and handle it. So that's the lazy guy's way out. You just put 0 in and you're fine. And 24 the index and no scan. And then trying to read an octet string is 110, again, 0 variation, index 1, no scan. Binary outputs are a little complicated, mainly because the electrical industry has different types of binary operations. They have pulses, and they have latch-ons, and they have complementary push-pulls, and all sorts. Generally, a simple digital on and off is a latch type, so you have to specify the latch type. And for outputs only, you must specify the variation, because that indicates exactly how we will write the command out. And most outstations will only accept the specific variation that they're configured for. So you have to be specific on the variation. We do have address assist on DNP3, tags connected to a DNP3 driver. So you don't have to remember all the numbers yourself. You can select them from drop lists and set the index there. Direct poll checkbox controls the :NS bit. So again, generally you don't want to set that. History file name again is for that WITS history read for the Xylem RTUs. So you just generally select from the group and variations, and then you have to enter the index or the index address, the register address of the item. Just showing the variation drop list there. The all variations is that variation 0 where you really don't care about it. A quick summary of the DNP3 communication modes as I see them. So we have this direct polling, as I mentioned, similar to Modbus. I don't think I've ever seen it used. I've used it in tests, but I've never seen it used in the field. You negate one of the big advantages of DNP3 there of being reporting by event if you turn on direct polling. Then we have the classic poll for events. So that's the check RTU interval where we poll for any events. And as I've mentioned before, if data isn't being notified by an event, then you have to use the integrity poll to retrieve that. The next step up from that is unsolicited events. So this is now where the outstation will send you a message when it has some event data for you. Again, up to the outstation configuration, what hold-offs you have, and so on like that. We will still poll the outstation at the check RTU interval, and we will still read static data at the integrity poll interval. And then the last one, as I mentioned briefly before, the disconnected unsolicited, particularly when using TCP, the master will poll for events, wait a little time, close the connection, so no bytes are being transferred. And I think this is very useful for cellular or anywhere where byte count is important because you're not using the communication medium. And then after a period of time, either the master wants to check again, so it will open up the connection, or the outstation has generated some events, and the outstation will connect back to you, and that's via the IP network listener tag, will connect back to you, you'll read the events, and then the connection will drop again. So in that's the most efficient use of your bandwidth there, that we're only actually connected up and running when we have data to send in either direction. A few quick tips. I think I've mentioned it before, but if you have analogs generating events, please set a deadband. Otherwise, you're just going to generate lots of useless events of your well level has changed by 1/8 of an inch. Nobody needs to know that. So sensible deadband. So that's a discussion you need to have with your customers. What's a significant event that they want to see reported? If you are using IP, I think this is a key one, prefer TCP over UDP. Yes, TCP will take up more bytes than UDP. And if you're in a byte-counted environment where every byte costs, you might be very tempted to use UDP. However, UDP, its proper name is User Datagram Protocol. I much prefer to think of it as the unreliable datagram protocol, because it has no resend mechanisms or anything else, and DNP3 doesn't specify any means to resend fragments. We have to resend the whole packet. So particularly I've seen it, customers running over cellular, using UDP thinking they're going to be saving bytes, but because UDP is dropping packets, or the cellular carriers seem to have fun with reordering the packets, you end up requesting and responding to much more. You send more requests and get more responses because you have to keep tossing away responses because they're not complete, because they're missing packets or they're out of order. And in fact, there is a DNP3 application note from the DNP3 users group that recommends not using UDP. As I mentioned before, for all the inputs, use the all variations 0. The driver will sort it out and quite happily reading all the variations. And then for outputs, you must specify the variation. I think I covered all these at the time, but comms tab, RTS key off delay 0, message fail time 0, retries to 0. I think I covered all those at the time. Yeah, that last one. Don't set a local time box, unless you like odd things at DST end. Well, thanks very much for coming. I hope you got something out of this, and I hope you have a great rest of the day and conference. Thank you.